Hey everybody, welcome to today's lecture for robotics. Today's lecture focuses on coordinate frames and transformations. So the first question you'd probably have at this point is what? What are we talking about and why are we talking about it? Okay, so the first thing I want to talk about is when we're working with robots, how do we specify position? In fact, when we're working with anything, how do we specify position? Well, if we were working in 2 dimensions, we could specify position as some xy coordinates. And then the question would be, what is this relative to? Well, it's relative to some axis, right? You've got an x-axis and a y-axis, and your coordinates are relative to that. Okay. When it comes to placing an object in space in 2 dimensions, we also have to keep track of the orientation of the object. Okay, so it's important if you're working with a robot to keep track of which direction the robot is facing. So in this case, you can see we've got a robot that has an orientation of 30 degrees and is at position 1, 2. So we refer to that tuple as x, y, and theta. Okay, now that's pretty cool. That identifies where our robot is. Is that sufficient? Is that enough coordinate information to allow us to control a robot? Let's look at an example of the AR drone, which you guys have been working with to do your PID control assignment. Okay, so let's say we've got 3 axes, X, Y, and Z, right? So if you applied some force along X, right, you can see the red line is X, the same red line is X in the world. And then you've got your Y, which is the green line, and your Z, which is the blue line. If you're applying some force along X, what would happen is the robot, the robot would move along X, right? Makes perfect sense. You apply some force along X, the robot moves along X. And this is useful because you can figure out what your target is in the world and you can apply a force in that direction and you can go that way, which is great. But what happens if the drone rotates, right? So if you look at what happened to the drone, it was facing straight and then it rotated so that it's now facing this way. Okay. Now what's interesting is if you apply a force along X, the drone's going to go this way, right? Which is a bit problematic because in the world, X is this way. So the complication is that there's now 2 x-axes. There's the world's x-axis, which is the one we care about, right? When we talk about the position of the drone, we care about where it is in relation to the axes of the world. But the drone, when we apply some control, it moves along its own x-axis, right? The x-axis relative to the robot. So the problem is that the target and the source are specified relative to the world, but the control is specified relative to the robot. Okay, so you can see the control is being applied here, but like along this x-axis with the y-axis this way, but the world has the x-axis this way and the y-axis this way. So the problem is we call these reference frames. So the robot has its own reference frame and the world has a completely different reference frame, right? So the problem is that we're applying our control in one reference frame and that's rotated compared to the reference frame of the world, which is the one we use to capture our errors and generally the one we care about in terms of specified position. So we sort of have a situation like this. We have our world axis denoted by the solid axes, and then rotated by an angle of theta, we have our drone's axis, right? Our robot axis, okay, or our robot reference frame. So the question becomes, if we sent our drone forward along its x-axis, what would that do to its position? Okay, so let's say the drone is at 0, 0. Okay, the drone is currently sitting here. If I move v units along the x-axis, where will the drone be then? Well, we can use a bit of trigonometry. So we know that this angle is theta. We know that this is a right angle. And so we can say that the sort of the movement of v along the x-axis of the robot causes a movement of v cos theta along the world's x-axis and v sine theta along the world's y-axis. Okay, can everyone see why that is? If not, feel free to message in the groups, but do think about it a bit. This is sort of a standard trig at this point. So if we, what happened here? Yeah, okay. So if we talk about the position of the robot, we now have two specifiers for the position. We have its position specified in the world's axis and its position specified in the robot's axis. Okay, so let's call the world's axis axis 0 and the robot's axis axis 1. So we then say that the position in axis 1, so this notation of p superscript 1 is one we'll be using all the time. The superscript denotes which axis we're talking about or which reference frame we're talking about. Right? I'll use those terms interchangeably. So p in reference frame 1 is equal to v0. Right? We've moved v along the x-axis, so it's just v along. But p in reference frame 0, which is the world's axis, is v cos theta, v sine theta, right? If we had to put a dot here and specify its position according to this world's axis, it would be at v cos theta, v sine theta. Does that make sense? Why am I even saying that? I'm so used to lecturing live that I'm asking questions that only work live. Okay, but what that tells us is that if we have a v movement in x1, it results in a v cos theta movement in x0 and a v sine theta change in y0, right? So that's this. So anytime we move by v along the x-axis of axis 1, we end up moving along the x-axis of axis 0 and the y-axis of axis 0. And if we sort of look at our air drone example, it kind of makes sense, right? If I move along this x-axis in the robot's reference frame, I will move a bit in the world's x-axis, and I'll also move a bit in the world's y-axis. Okay. So our change in x1 results in a change in x0, and our change in x1 also results in a change in y0, and this trig defines the relation by which it moves. Now, what happens if we have a w change in y1? So we moved along the x-axis, but we also want to move along the y-axis, right? So I'm going to leave this as an exercise for you to do. Think about it. This angle will also be theta, right? Simply because of the 90-degree relation between these axes. So this angle will be theta. And so what would, if we moved w along y1, how much would we be moving along y0, and how much would we be moving along x0? Okay, so pause the lecture here and see if you can work out what changes in x0 and y0 will result from this w change in y1. Okay, hopefully you worked out that a w change in y1 results in a w cos theta change in y1 and in a minus w sine theta change in x1. So you can see moving up in the y-axis, so in a positive direction along the robot's y-axis, resulted in a negative movement in the world's x-axis. Okay, so so if we were to try and express this, we can say that x1, which is the x position in the robot's reference frame, will become v because I've moved v along the x-axis, and y1 will be equal to w because I've moved w along the y-axis of axis 1, and x0 will become v cos theta minus w sine theta, right? This is because we've moved along x by v cos theta because of this v movement, but then we've moved backwards by w sine theta because of this w movement, right? So the final x0 will be v cos theta minus w sine theta, and y0 will be v sine theta plus w cos theta because we'll have moved by v sine theta because of the v movement in y0, and we'll have moved by another w cos theta because of the w movement in y1. Okay, so we could swap out the v's and w's for x1 and y1, right? This is a system of simultaneous equations. And we end up with x naught equals x1 cos theta minus y1 sine theta, and y naught equals x1 sine theta plus y1 cos theta. And it's often convenient to convert this into a matrix representation just because then our calculations are easier and it's easier to remember everything. Okay, so we can restate this system of equations as x naught y naught equals cos theta minus sine theta cos theta x1 y1, right? Basically what we've now done is we found a linear transformation that converts from coordinates in reference frame 1 to coordinates in reference frame 0, which is pretty cool, right? Because it means that at any point, if we have coordinates in reference frame 1, meaning coordinates relative to the robot, we can convert them to coordinates relative to the world just by applying this linear transformation, right? Just by pre-multiplying them by this matrix. This matrix is quite a useful matrix. We call it the rotation matrix because that's what it does. It rotates these coordinates to give us these coordinates, right? And we'll particularly call it R1 naught, right? It's the rotation matrix that converts from reference frame 1 to reference frame 0. That's the sort of notation convention. And the cool thing is we can say the position in reference frame 0 is the rotation matrix that converts from 1 to 0 multiplied by the position in reference frame 1. Okay? So yeah, R1 naught is our transformation from reference frame 1 to reference frame 0. Okay, I hope that all made sense. It's about to get a little bit more interesting. Let's do an example. So if we said that reference frame 1 was rotated by 90 degrees relative to reference frame 0, so in this case, the drone rotated by 90 degrees, right? And we know that the position in reference frame 1 is 2, 1. Can we find P naught? Okay, so that's another exercise I want you guys to do. Again, if you pause the video and do it, that'll be useful. I'm not gonna give a solution in the lecture, so yeah, just play with it, see what you get. Okay, so that was pretty cool, except that our drone was in 3D, right? So how do we do this transformation stuff in 3D? Well, the important thing is that how we record 3D rotations is we actually record them as rotations around a particular axis. Okay, so we don't sort of rotate in 3D space all at once. We rotate around a particular axis, or we rotate a particular plane. So if we were to rotate around the z-axis, you can picture this as you've got your three axes, your x, y, and z, and you remember that blue line that defined the z-axis. Picture yourself holding that line and kind of twisting it so that the world rotates, right? And if you picture that, what actually happens is that, you know, z sort of stays where it is, and x and y rotate around, right? Again, picture this sort of structure. If I was holding on to this blue axis and I just sort of twisted in an anti-clockwise manner, I'd end up like there. You know, I'm sort of rotating around the z-axis. Okay, and if I rotate around the z-axis, I'm pretty much doing the calculation I just did, right? I'm rotating my x and y. What happens to z when I rotate around z? If I said that the drone was 2 feet off the ground, and now I rotate, why did I say feet? 2 meters off the ground, and we now rotate around that z-axis, what would the z value be? It would still be 2, right? Because I haven't done anything to the z-axis. So if we're rotating around z, there's no transformation needed between z1 and z0. z1 will be equal to z0. Okay? So if I still wanted to phrase this as a rotation matrix, if I still wanted the relation that p0 equals r1 naught p1, x0 will be x1 cos theta minus y1 sine theta. That's the same. That's what we did in 2 dimensions, right? y0 will be equal to x1 sine theta plus y1 cos theta. Again, same thing we did in the 2D rotation. The only addition is that z0 will be equal to z1, because we rotated around z, so nothing happened to z. So we can now restate this as x naught, y naught, z naught, cos theta multiplied by x1. So we've now got a rotation matrix. And if you confirm what happens when you do this multiplication, you'll find that this is the sort of matrix representation of this system of equations, right? This 1 means that z1 gets preserved, and these zeros means that z1 doesn't really affect x naught and y naught. Okay, so we end up sort of with the same rotation matrix we had earlier, but extended to 3 dimensions. Okay, and that's great if we wanted to rotate around z, but sometimes we might want to rotate around x or y. But the point is they're exactly the same. You're going to do exactly the same trig, just with transposed axes, right? So rotating around x by theta gets us this transformation matrix. Rotation by y around theta gets us this transformation matrix. And the rotation around z by theta gives us this one that we've already seen, right? So when we rotate around x, you'll see that the x value will be unchanged, right? If you pictured multiplying this matrix by x naught, x1, y1, z1, you'd find that x1 would get preserved because of that one. And your transformation, the same transformation you have here, will actually be applied to y and z, because now we're rotating in the yz plane because we're rotating around x. And similarly for y, right? So we can rotate around any of the 3 axes, and the operations are pretty much the same. So that's pretty cool. That helped us deal with rotations. There's also a problem in that axes can also be offset. What I mean by this is that the origin of the axes is not necessarily on top of each other. You remember the diagram we had earlier? We had this robot axis on top of the world axis, right? The origin was at the same point. But what happens when the drone moves? Well, when the drone moves, let's say we moved in this v direction, the drone ends up at a new position. Let's call it dx dy. So that the reference frame 1, or the robot axis, is now both rotated, right, by some value theta, as well as translated. So it's also moved by dx dy. Okay. So if I know a position relative to the robot, like so there's some coordinate here, how would I go about translating that back into the world reference frame, which, remember, is again the one I actually care about? So it's quite simple, actually. We know how to translate coordinates based on the rotation, right? So we previously had x naught equals x1 cos theta minus y1 sin theta, and y naught equals x1 sin theta plus y1 cos theta. And all we do now is we add the dx and dy, right? So if I had a point in space here somewhere, I first deal with the rotation exactly as I've dealt with the rotation before, and then I add dx and dy so that to give the correct coordinate in the world reference frame, right? Does that make sense? Like if I know that I'm at position 1, 2, say, okay, then the first thing I do is rotate the axis the same way I would have rotated it, and I'll get some value. Let's say, okay, it's not going to be a clean value, but I'll get some value. And then, according to where the world reference frame is, I need to add another dx and dy because I'm further along, right? The axis is actually moved. Okay, so I hope that makes sense. So x naught will be x1 cos theta minus y1 sin theta plus dx, and y naught will be x1 sin theta plus y1 cos theta plus dy. Okay, because I've moved along the axis as well. But if I still want the kind of format I had from the rotation matrix, I don't want to have to do these individual calculations. I want a nice linear transformation that I can just apply to the vector. Then I can actually kind of cheat. I can make a vector x naught, y naught 1 and x1, y1 1, and multiply that by my original rotation matrix augmented with the dx dy and a 1, right? And why I've augmented this with 1, this with 1, and this with 1 is because that allows this dx dy value to be preserved unchanged, right? If you picture multiplying this first row by this first column, you'll get x1 cos theta minus y1 sine theta plus dx, right? Similarly, for the second row, you'll get x1 sine theta plus y1 cos theta plus dy, which is exactly what we want here. And for the third row, we'll just get 1. So the cool thing is that this 1 here it just exists to preserve this one, so you can end up with the same format going in and going out. Okay, and sort of fundamentally what we're doing here is we're saying p naught 1 equals t1 naught p1 1. Okay, so we're using the notation t for a transformation rather than r, which was just a rotation. Okay, so this t1 naught is a linear transformation that converts from this augmented position in reference frame 1 to this augmented position in reference frame naught. So again, it lets us do that transformation with just a easy multiplication, right? And this is great because these transformations are something you have to do all the time. So it's nice that they're just simple multiplication. Okay, now if we're doing this in 3D, let's say we said reference frame 1 is rotated by theta degrees around z and displaced by dx, dy, dz. This is quite simple. What we'll do is we'll actually just do the same thing we did to the 2D rotation matrix, right? So you'll notice in the 2D rotation matrix, we took the 2D rotation matrix and we augmented it with our displacement value and we put zeros and ones so that the multiplication would work out. We're going to do the same thing here. We have our 3D rotation matrix. This part here, this 3x3 part, is the same rotation matrix we had earlier. We then stick the dx, dy, dz over here and the 1 over here for it to be multiplied by, right? So that the dx, dy, and dz will be preserved in our when the multiplication resolves. And we put a row of zeros followed by a 1 here just so that the 1 gets preserved in our next code when we do the transformation. So in this way, we can do a rotation and a displacement using the same linear transformation, right? So that's pretty great because it means we have just one matrix, our transformation matrix, that can do a 3D rotation and transformation. So if we have a coordinate in reference frame 1, we can translate it to a coordinate in reference frame naught just by pre-multiplying it by the transformation matrix. Okay, now this 3x3 portion was the rotation around z portion. If you have a rotation around x or a rotation around y, you can just use the appropriate transformation matrix, right? You don't have to use the one around z. So this 3x3 portion will change and you'll augment the other, let's say you'll augment maybe the one around x, you'll put your dx, dy, dz here and your 0, 0, 0, 1 here, right? So you can rotate and translate around any axis you like. Okay, now the other cool thing, and possibly the last cool thing we're going to talk about for this, is that you can stack these transformations. So let's say I had a situation where I said reference frame 1 or axis 1, what we were calling the robot frame, is rotated by theta degrees around z and offset by dx, dy, dz. So I can make some t1 naught that represents this rotation and transformation, right? And then if I said reference 2 is rotated by alpha degrees around x and displaced by qx, qy, qz relative to reference frame 1, I could then construct a transformation matrix that goes from reference frame 2 to reference frame 1 the same way, right? I use my my alpha degrees around x to get me a transformation matrix. I augment it with my displacement, which in this case is qx, qy, qz, and I get a transformation matrix, right? Now there's a couple of relations that are interesting here. The position in reference frame naught is the transformation in reference frame from reference frame 1 to naught multiplied by p1, right? So multiplied by the position in reference frame 1. Similarly, the position in reference frame 1 is equal to the transformation from reference frame 2 to reference frame 1 multiplied by the position in reference frame 2, right? So sort of this 1 and then you get transformed out to naught. Similarly, this 2, you get transformed out to 1. But interestingly, if you just substituted this equation for P1 in the top one, you'd get that P naught is the transformation from 1 to naught multiplied by the transformation from 2 to 1 multiplied by the position in reference frame 2. So you're sort of taking this position in reference frame 2, transforming it into reference frame 1, and then transforming it into reference frame naught in one step. Now, if you often have to perform the same transformation, you can just combine the two transformation matrices to produce a T2 naught, right? So if you just sort of took this and multiplied it, then you can end up with T2 naught equals T1 naught multiplied by T2 1. And then you can say P naught equals T2 naught P2, right? That's a useful thing because now anytime I want to convert from reference frame 2 to reference frame naught, I can do it with one multiplication because I've sort of pre-multiplied these two transformation matrices out into this big matrix. Okay, so this comes in handy when we're working with robot arms, right? Simply because robot arms have a lot of joints. So what you find is that you can know the position of one joint relative to another joint, and then that joint relative to yet another joint, and that joint relative to the world. So you're moving in multiple reference frames, and we'll cover that next week. I hope this wasn't annoyingly opaque, but feel free to message and hopefully we can resolve any misunderstandings. But yeah, I hope that was fun and interesting. Thank you, everyone.